The broadcast is now starting. All attendees are in listen-only mode.
We're starting on time, so let's start. Okay, good morning, everybody, and welcome to the fifth in our series of talks on artificial intelligence and machine learning. These talks are jointly sponsored by Metron and George Mason University. Our talk today will be by Professor Nick Polson of the University of Chicago, and it's titled AIQ, How Humans and Machines Are Smarter Together. And it's based on Nick's book, AIQ. And I've read the book. It's very enjoyable read. And for those of you that are not experts in machine learning, this is a very good way to get into the topic. He does a terrific job. So it's a little bit of background on Nick here. Nick is a Bayesian statistician, so this is in the right place if you're a Bayesian statistician. Conducts research in financial econometrics, Markov Chain Monte Carlo, particle learning, and Bayesian inference. Inspired by an interest in probability, Nick has developed a number of new algorithms and applied them to the fields of statistics and financial econometrics. His article, Bayesian Analysis of Stochastic Volatility Models, was named one of the most influential articles of the 20th anniversary issue of the Journal of Business and Economic Statistics. And his recent work includes methods for sparse Bayesian estimation, the application to high-dimensional regression and classification. Again, out of great interest around here. So, Professor Polson.
Thank you so much, Larry. Okay, thank you very much for having me, and thank you for coming to my talk. So as Larry said, one reason I'm here is to try and sell my book. I realized being an academic, I'm not very good at marketing. So I wrote a book with a very good friend of mine, James Scott, who sort of has a unique ability to make these ideas accessible to the general public. There's also an Italian version, believe it or not. So if you want to know what AI translates to in, I guess that's what intelligent numbers. That's the Italian version. And maybe you can't see the one over here on the other side, but this is the Swedish version of the book. So you can see how other cultures translate the book. Actually, it's had a number of unintended consequences that I hadn't realized. One was that all of my academic friends, it's generally their spouse that reads the book. So I was rather hoping that my academic colleagues would read it, but generally the wives of my professor friends have read it. They all love the book. And when I ask my academic friends if they read it, they all come and, oh no, haven't had time to read it. So maybe Chris can buy a copy for his wife or his kids or whoever else, and they can read the book and explain it to Chris. So I thought you'd find that quite amusing. Anyway, so spent a lot of time. Hope at least one or two of you buy a copy of the book and enjoy it. Let me just quickly tell you what's in the book. So I've got one slide of what's in the book. There's actually 7 chapters or 7 vignettes of 7 different people. And I guess one reason that I was so excited when Larry emailed me and said, oh, Nick, can you come to Metron to give a talk, is one of the chapters is about finding the USS Scorpion. And so I was very excited to come here and talk to Larry about his work on, your work on the Air France planes and all these other things you've done. So chapter 3 is about finding submarines. Oh, and I should make one other comment that I've actually been teaching a number of years of my life, and so I love to teach Bayesian stats. And I've got a whole bunch of examples in marketing and finance and econ and engineering, all these other fields, right? Of all of the examples I've ever done, the one that the students relate to most is finding the submarines. So I'm not so sure what it is, but the second that they realize that you can use Bayesian methods to find something under the ocean, I don't know what it is, they just find that just so absolutely incredible, right? So a lot of my students, the second they see that, they're like, why would I ever go back and do anything else, right? So I thought you'd also find that interesting. So today's talk, I want to cut it into 2 halves, and if you've got questions, stop me. So maybe I'll even finish a little bit early because I'm much better to find questions. I've cut my talk into 2 halves. So I want to talk a little bit about the book, and I want to do one of the simple examples up here, this Abraham Wald it's a World War II example. This is a famous example, so I want to do 3 or 4 slides on that. And in the second half, at the moment, I'm doing my research in deep learning. So I just wanted to do 7 or 8 slides and sort of put up some of the types of papers that I work on in deep learning. So if you have questions afterwards about deep learning, I would love to answer that too. So as I said, there are 7 chapters. Abraham Wald, somebody called Henrietta Leavitt, who was an astronomer, John Craven, finding the submarines, somebody called Grace Hopper. There's actually, if you go to Google and type Grace Hopper, the first thing you'll find is the David Letterman interview when she was like 92 years old of David Letterman. So maybe there's hope for Larry yet. When he's 92, he'll have a David Letterman talk with Letterman's at 100 and whatever. Anyway, so there's a very fun interview with Grace Hopper. She basically invented the compiler, so in the 1950s. I think that's sort of interesting. I was originally English, so there's an Isaac Newton story. I don't know if you know, but Isaac Newton, we call it the master of the mint. You call it what? Federal Reserve chairman. So Isaac Newton controlled the money supply in England, amongst other things. And one thing he did was he put England on a gold standard. Actually, there was a trade war between England and China in 1720, maybe this story will resonate. We used to trade silver to the Chinese, and they would give us back lots of spices. So the price of silver was 6 times as high as the price of gold back in 1720. And of course, when Isaac Newton came into the mint, he thought, well, why don't we just switch things around and put us on a gold standard, not a silver standard? Well, that sort of annoyed the Chinese because the price of silver went from like £50 an ounce to close to 0, right? And the price of gold went from close to 0 to a high level. So all the gold that the English had taken from the Spanish in the previous century that we had in our vaults of the Bank of England became, you get the idea, right? So the tool back then was the price of silver and gold. I guess the tool today is what? The Twitter account or whatever happens. So trade wars with China have been going on a while. One thing that Isaac Newton got wrong is that he didn't know how to do standard errors. So when you read this chapter, you realize he made gold coins, and of course the English public would clip the coins. That'd scratch a little bit of gold off, right? Don't trust anybody from England, by the way. In English. So they would clip the coins, and of course they would take 1,000 coins and weigh them to try and figure out how many coins are being clipped. Right? And when Newton did that experiment, he didn't realize that if you weighed 1,000 coins and you wanted the standard error for an average, it's x bar plus or minus sigma over root n. So he forgot to divide by the square root of 1,000, which made a pretty big difference, right? So he was letting all these clipped coins go into general circulation that he shouldn't have really done so. So since then, English currency for the last 300 years has gone down in a straight line. But, I'm blaming Isaac Newton. I guess I had to have one chapter on sports analytics. So there's a Joe DiMaggio chapter. There's also another interesting chapter on healthcare analytics. And I know you guys don't do healthcare, but it seems as if the next area that people want to move into in machine learning is healthcare analytics. And from the Crimea War, the 1850s, Florence Nightingale was a nurse in the Crimean War, and she was really the first person to collect healthcare data on deaths. And actually, she became a fellow of the Royal Statistical Society. So if you're a statistician in England, becoming a fellow of the Royal Statistical Society is the ultimate honor. And she would actually come back and give lectures to all the professors about healthcare statistics. So if you go to the journals, the Royal Statistical Society has been going for a while, you'll see Florence giving talks to all these professors of statistics. So she was one of the first people that was into healthcare diagnostics. So there's 7 chapters on 7 people. And, over here, the key ideas and key concepts, right? You'll see Bayes' rule there a lot. You'll see big data, you'll see AI, you'll see probability, all the kinds of things that you guys work on. So there again, there's the list of.
Craven is dead.
Craven, yes.
Yeah.
So I should have added it. So that's a list of 7 people. As I said, I just want to do 10 minutes, 15 minutes on Abraham Ward, and then I want to talk a little bit more about deep learning. So let me just talk a little bit about AI, right, at sort of the lowest level that I can think about, right? So to me, why is there this boom in AI right now, right? I mean, I remember when I started my career as an assistant professor at Carnegie Mellon, and they were always talking about AI. There was somebody called Herb Simon that was there that was always talking about it. Why now has this increase happened? Well, partly because of the web, right? Partly because of incredible data collection, and partly because of algorithms or apps, right? Every app you've got on your phone is like an algorithm, right? And I think you guys know this one too. Algorithms, what's the key insight is that they really deal with probabilities, right? So, what's the most likely movie you want to watch on Netflix? What's the next video you want to watch on YouTube? Right? What's the probability I'll make it into DC tonight to see my kids for dinner, right? The traffic problems, right? And so the growth of the web is really synonymous with the growth of probabilities, right? Or algorithms. Give me an input, give me an output, right? And of course, this is where Bayes' rule is going to come in, right? Or conditional probability is going to come in. So to me, that's why Bayes has become so incredibly important, that anything that Google does, Facebook does, Amazon does, all of these kinds of things are sort of probability assessment machines, right? Okay. And just a couple of other, I could spend a long time talking about this one too, sort of an interest of mine. People would always talk about Moore's law. I mean, I remember when I bought my first hard drive, a 1 gigabyte hard drive cost me $1,000, if you can believe that. I had like a smart workstation. 1 gigabyte was $1,000. Now 1 gigabyte is like 0.0. It's gone the other way, right? So storage has basically not become infinite, but storage has become huge. The speed of the chips got faster and faster. Every 18 months, the speed of the chips would double. So that was Moore's law. Well, in some sense, Moore's law is sort of stopping, right? Harder and harder and harder to put more transistors on a chip, right? Harder and harder to double the speed of these Intel chips or AMD chips. So along came companies like NVIDIA and Google that started to do chips that could handle images and tensors. So Google is the master of these things called tensor processing units, so instead of CPU, TPU. So how can you very quickly manipulate a tensor? NVIDIA is very good at image processing. How quickly can you manipulate an image? Graphics processing units. So in some sense, there's also a relationship between these algorithms and the chips. People are even coding in, if you like, Bayes' rule into the chips, so you can do things faster and faster. So for me, it's, we had 30 years of Moore's law, which is sort of going away. The new Moore's law is an infinite amount of data, and then also this computational power that we have that's behind it, right, is, to me, is quite incredible. So I think that's also a reason why people are interested in AI. Okay, so let me just do this very simple Abraham Wall example. It's one of the stories in the book, so it's a simple example, but I think it's got a good message for us. And so, why do I like Bayes' rule? Well, it always seemed to me as if every probability I'd want to work out is a conditional probability. It's just, what's the right question? What's the right conditional probability that I need to work out? So a World War II example, all of these planes would come back to England, and you'd see that there'd be lots of holes in the fuselage of the plane. Right? So a certain number of planes wouldn't come back. There'd be lots of holes in the fuselage of the plane. And the way people typically tell the story is counterintuitively, right? If you see lots of holes in the fuselage, maybe we should reinforce the fuselage, right? But if you think about it, that's not really the right answer, right? Those are the planes that made it back. So counterintuitively, you should put the put the reinforcement under the wings of the plane. So if you go to Google, that'll be the story that people will tell. There's a counterintuitive. Well, it's a bit more than that. So I think the thing I want to say here is that if you go back and read the original academic paper that Ward wrote, he did a lot more than just that simple counterintuitive thing. He came up with a very careful probabilistic analysis of what these missing data question marks are, right? So there's a lot of work into figuring out what those missing question marks were, right? I mean, actually very similar to the kind of work that Larry does with his probability maps for finding things. You know, if there's data I haven't seen, how can I somehow fill in the missing data, right? So of the 316 that returned, you can see where the damage was. What you really want to know are these question marks, and there's a lot of work into figuring out what those question marks are. Right? Now, again, Bayes' rule, right? You've got to get the right conditional probability, right? Most people are like, oh, probability of damage on fuselage given returns safely, right? So fuselage was what, 105 out of 316. So what's the probability of damage on fuselage given returns safety? 32%, right? Well, if you think about it, right, that's the likelihood function, right, in likelihood parlance. You want it reversed the other way around, right? You actually want to know what's the probability to return safely given damage on fuselage, right? Now, if that's a low number, I'm going to put some reinforcement on the fuselage. If it's a high number, I'm not going to reinforce the fuselage, right? So two totally different probabilities, right? This is the Bayes one. This is more like the likelihood one, right? And again, it's going to depend on Wald's model of how he filled in the missing blanks. I'm not going to give you the, it's an academic paper. There's a nice discussion in one of the statistics journals called JASA that shows how he managed to fill in those missing data problems. And now I want to work out the Bayes probability, right? Probability to return safely given damage on fuselage. So what do? I go into the box of fuselage, 105 and 8. I can ignore all the other numbers. So there's a total of, 113 cases. And I just reproportion the probability, 105 over 105 plus 8. Oh, it's 93%, right? So again, that counterintuitive, the planes that came home with damage on the fuselage is, yeah, they're highly likely to make it back, right? We're not going to reinforce the fuselage. We're going to go and reinforce the wings of the plane. So statistically speaking, we'd call that a missing data problem or an imputation problem. And it's everywhere in Netflix and in Google, right? If Netflix is going to recommend a movie to you, I think the next slide, I talk a little bit about Netflix. It's a movie you haven't seen before by definition, right? So how does it fit in the missing data, right? How does it know how likely you are to watch a movie, right? I think the first application that was Amazon. One of my old colleagues from CMU went to Amazon and did something called Book Matcher. You guys won't remember this, but it was a huge invention back in the day. What book would you like to buy given the sequence of books you've already bought, right? So Amazon was really the first company to do these recommender systems. Nowadays, it's coming to a level. So nowadays, all these models would be what's known as deep learning. So, and we'll get to deep learning. Deep learning is a very clever way of picking out nonlinear structures in problems. So, a modern-day version of the Ward problem would be Netflix. Geez, again, I'm talking about the book. Maybe I should hold it up again. All right, let me. Please buy a copy of the book. I think I'm number 125,000 on Amazon, right? So I figured if everybody in the room buys the book at exactly the same time, right? The machine learning algorithm in Amazon will think, oh my God, there's going to be a massive inflow of orders, right? So we have 30 people buying a second. They'll be like, there's going to be, 25,000 copies bought by the end of the day. And so anyway, if I sell 2 books, my mission would be succeeded, right? So there's a whole bunch of, James and myself, many hours of discussion, and there's lots of incredibly interesting, strange problems in there. From Henrietta Leavitt problem, She was one of the forerunners of Hubble and Hubble's work. So she was an astronomer, or there was Zillow. How does Zillow price your house? I used to talk about this with students, and they would tell me, "Oh, Zillow sucks. It doesn't get the price of my house anywhere near." Well, as the years have gone by, every time I say this, they're like, "Oh my God, I don't believe it. I just sold my house and Zillow had the price within 1%. So these algorithms, the more and more data, the more and more transactions, the better they are. So what's also funny to me is that people are beginning to realize that some of these algorithms are actually coming up with useful stuff. Oh, there's a strange one down here, how to sort cucumbers. There was a Japanese cucumber farmer, and apparently there are 9 different types of cucumbers. It's an image recognition problem. And he would grow his cucumbers, and his mother would have to sort them. And it was an 8-hour job to sort these cucumbers. Well, what did this Japanese farmer do? He downloaded TensorFlow, which is a Google program for doing deep learning pattern recognition. Like 10 lines of code, coded up an image processing algorithm for classifying the 9 different types of cucumber. Built a little camera, a little machine, automatically did it. So what was the consequence? His poor mother, who enjoyed sorting cucumbers for 8 hours a day, was out of a job. So the story's in the book. So what's been happening, right? And I think this is actually interesting for given that I grew up as a statistician, right? And maybe this is a topic we can discuss later, right? Is a lot of AI and machine learning has become a pattern recognition game, right? Larry was talking about imitation learning. There's lots of different words they use for these things. So just collect a big database, right? Collect a database of 10,000 images of cucumbers, right? Where they're labeled 1 to 9, right? Fit a deep learning model to it, so no need for theory of how cucumbers grow or whatever, and pattern match, right? Do some kind of out-of-sample cross-validation of your 10,000 observations, keep 1,000 aside, check to see how well I do, how many type 1, type 2, or false positives, false negatives, and just pattern recognition everything, right? And that seems to me to be something that growing in a very big way. Deep learning is sort of central to that. I've got one slide on what my stats friends do. So if you grew up as a statistician, you would see all these acronyms, right? Sliced inverse regression, generalized linear models, generalized additive models, principal component regression. Jeff will go, what about projection pursuit regression? What about PCA? What about PLS? I could now not do one of those. I could now go down 50 methods if I did it really quickly, right? Well, the stats guys, in their infinite wisdom, well, maybe except for sliced inverse regression, is we spent too much time doing additive models. So my joke to my stats friends is, yes, we know how to add things, right? What we should have done is compose functions. So in a second, I'll show you the deep learning slide. Deep learning side is a composite, f of g of x, right? Not f of x plus g of x, right? And so deep learning is like a sequence of filters, right? So suppose I want to find out whether there's a cucumber in a picture or not, right? I'm going to do something called a convolutional neural net. Well, that's just a filter, right? Then I'm going to do something called a rectified linear unit to classify. That's another filter, right? I'm going to do a sequence of filters, a composition of functions, right? So, yes, so I'm very good friends with somebody called Peter McCullough that invented generalized linear models. I'm like, Peter, all you had to do was to put another function here in. He was like, Nick, I'm too old to do that now. But he wished he had, right? He wished he'd done composites of functions, not just one function of a linear combination, right? So in some sense, all these old statistical methods are only trying to find additive structure, not composite structure. And a lot of these problems that we're doing have composite structure. What movies you like, what videos on YouTube you like, how you would price something on Amazon, ... Composite structure, not additive. I'm sure you've heard about trees. I'm sure you've heard about cart. I remember going to the original talks that Jerry Friedman and Bryman gave on cart and random forests. Actually, at the time, I thought, this is ridiculous. Why would anybody fit tree models? So I was wrong about that one. I once went to a lecture by somebody called John Gittings, a very famous professor that did bandit problems. Something called the Gittings Index, multi-armed bandit problems. At the time, I was like, no one's ever going to use this. Well, if you go to Google, everything, or Alibaba, everything is an A/B test with multi-armed bandit trials. It's become one of the biggest things in sequential decision making. So I guess I'm 0 for 2 there. I went to a talk by Jeff Hinton when he was at Carnegie Mellon about deep learning. I went, he shouldn't do that. He should really do MCMC. So I'm 0 for 3. So the reason I guess I'm telling you these things is just like my stats friends back here, right? I'm just doing additive models. Sometimes it's not easy to see what the new technology will grow into, right? Now, again, maybe, on the other side of my hat, right? Machine learning has grown so quickly that they seem to always sort of jump to the answer, right? I think in some sense, machine learning would do very well to step back and do a little bit more probability accounting and do a little bit more Bayes, right? So I think at some stage of their life, they'll fall down on this, or I'm just making predictions. And at some stage, they'll want to have more interpretable models, and at some stage, they'll want to go back and do more Bayes. So I still think maybe I shouldn't make a prediction, but Bayes inside machine learning, I think, will still grow. Let me I hope so. See what's going to happen. Yeah, maybe this slide is useful or not useful for us, but it's this composite of transformations, right? So you'll see me do x, phi of x, a of phi of x. So we do lots of composite transformations, right? So one of the clever things I think in machine learning for how these deep learning models work from a stats perspective is you'll start off with a bunch of predictor variables. You'll do some nonlinear transformation, and maybe you estimate this nonlinear transformation from training data or imitation learning to create something called characteristics. This is an example from, this is a credit scoring example, one of the original examples. Then from those, you'll do another nonlinear function of a nonlinear function to create something called attributes, maybe introduce dummy variables, ... Then you'll maybe segment into classes, so you'll do another function on top of the function. I guess it should be what, f1 of a of phi of x1. So you're continuously doing different filters, right? So you start with your predictor variables, you convert them into characteristics, convert them into attributes. You'll then segmentate into the different groups, maybe the 9 different types of cucumbers, and then you'll run some regression at the end of the day, right? So the stats bit will still end here at the end of the day, right? You'll still have to figure out how to weight your nonlinear transformations of the x's. So I think that's becoming a much more popular approach for doing all of these problems: image classification, even natural language processing. Now, another slide of math. Why does that work? Why does composing functions work? Well, I work with somebody called Vadim Sokolov. I think Vadim came and gave you a talk. So Vadim loves anybody that's Russian, of course. So if I ask Vadim, well, who originally did this? Of course, Vadim will say Kolmogorov. So there's a very interesting theorem. So maybe just the answer is interesting. There are really no multivariate functions. So suppose I want to have some function of many variables, right? There's just superpositions of univariate ones. So it's a very strange theorem, right? So f of x down here, x is just a vector of maybe 1,000 variables, maybe 1 million variables, right? Well, I can generate f as a composition, so a circle for composition, f1 of f2 of f3, not an additive model. And the little f up here is just a univariate function, like the maximum function or the logistic function, right? And here I'm just running a regression, or I would call this a semi-affine function, right? So here's what I do, right? I start off with x. I first of all run a regression at the first layer. I then apply a little univariate activation function. I then take this as an input into the next layer. So then I run another regression, another activate, ... right? So one reason, back here, I hope this slide was clear, one reason why cutting my data set up this way or transforming it by a sequence of nonlinear functions before running my stats model at the end, now why does that work? Well, I can basically get any multivariate function I want. Right? And that's what deep learning is, right? So that's so in 2 slides, I think I've done my best. A lot of people are confused as to what deep learning is, right? What deep learning is just a composition of semi-affine functions for modeling high-dimensional nonlinear structure, right? And the machine learning guys are clever, right? They take a huge data set, they just take a bunch of XY pairs, 100,000 images in the ImageNet, right? So about, maybe 1,000 different categories, right? Cats, dogs, rabbits, ... right? Submarines. I want to find a submarine. Just take a massive data set. Now there's TensorFlow. What does TensorFlow do for you? TensorFlow essentially estimates the weights and the offsets, right? You have to tell it what the lefts are, but you usually just put something simple in, right? Like the logit function if I'm doing classification, or the rectified linear unit function, or the maximum function. So you put very simple functions here. TensorFlow does all the hard work. How many terms? What are the weights? What are the offsets, right? And that's a clever optimization problem that they've solved, right? Okay, so as I said, maybe I'll do 10 more minutes and leave plenty of time for questions. I've written a whole bunch of papers on this, and sometimes I hate it when people do this, right? So in academics, you would never do this, right? But Google has everything, I've realized. So I've now realized there's no need for, just like the Japanese cucumber father's mother, right? There's no need for professors anymore. You just go to Google and type in what you want, and it gives you it immediately, right? So I think at some stage of my life, there'll be no need for professors, right? So I'm doing the opposite, right? I went to Google, I typed in my name, and I went, what does Google know about me, right? And up come all my papers on deep learning, right? So I've written a whole bunch of deep learning papers, and if you want to talk over lunch, I'd love to. So, I wrote in 2015. So I think I was the first person to write a paper on deep learning for finance. So hopefully at some stage of my life, somebody look back and say, oh, who was the first person to do deep learning for finance? And
are you dealing with hedge funds? I mean, who's the client? Yeah, and you talk to actual hedge funds, and are you trying these algorithms?
Tom, you have to realize that being an academic, the client is myself. Right? It's like a confusing concept, right? But I do love the stock market. So I do fess up to having spent. I didn't know what a stock was until I came to this country. I came to this country when I was 23, and I think I learned too much about stocks when I was 24. So I do like the stock market. But yes, these things I tend to do for myself, right? For better or for worse.
We did some of this more classical methods for a couple of hedge funds. So we can.
Yeah. So Jim Simons, the Renaissance technology. I think Jim Simons was the original guy that understood.
We're not quite as successful as he was.
Actually, the guy that did Jim's algorithm is a guy called Lenny Baum. Do you know the Baum-Welsh algorithm? 1970, common filter for discrete state spaces. So annals of mathematical statistics. Lenny Baum worked with Jim, and he was the first guy to do hidden Markov models for trading. So yes, you're right. If we went to Wall Street, 2 Sigma would say, oh, geez, yes, deep learning. Yeah, my guess is that deep learning in hedge funds will grow. But again, geez, I'm 0 for 1. I'm 0 for 4. I'm making all these predictions that you should test it after sample, right? So, yes. Anyway, I'm very, very happy with myself for writing the first paper in deep learning in finance, right? There'll be like 1 million papers afterwards. There's Vadim. Vadim's wonderful, as you know. So we did deep learning for traffic flow prediction. Actually, before that, we wrote deep learning using something called the fundamental diagram in traffic flow. So solving partial differential equations. So before there were sort of stochastic models of how traffic flows, right? And we had great fun solving these nonlinear partial differential equations and fitting it to data, right? Well, at the end of the day, having done that project, which took like a long time, years, we just threw it into deep learning and got much better results just by pattern matching. So I also write papers where my previous papers become obsolete, right? So I will let you know if I write a finance paper that makes deep learning obsolete. So deep learning is, so this paper here has way more sites than the deep learning paper that did the partial differential equation approach. Again, I've done some Matthew works in high frequency trading type stuff. So yeah, so I guess I've done finance, I've done transportation problems, I've done some spatial data problems. Anyway, so you can see what I get up to, right? And there's like an overview paper that I wrote with Fadi. So, and there's, geez, I'm sure in the next year I'll write another 4 or 5 deep learning papers. I'm still addicted to writing about deep learning. Okay, I think I'm getting near the end. If you're reading the book, back to the book, chapter 5. I actually describe deep learning. So if you want your kids to know what deep learning is, it's the Henrietta Leavitt example where she was looking at images of galaxies. Okay, maybe I'll jump a couple of slides because I want to leave plenty of time for questions. Geez, I mean, you know, AI interpretability is becoming a big topic. AI ethics is becoming a big topic. There's a very famous case in Germany where somebody went in to buy Mercedes-Benz and he talked to Katerina on the phone about what Mercedes-Benz he wanted to buy, right? And of course, Katerina was actually a chatbot. It was just a machine. And he kept on asking the salesman of Mercedes-Benz, no, I need to talk specifically to Katerina. It was incredible how she knew exactly what I wanted, what color I wanted, specifications in the car. He was just so impressed with her knowledge of the car that he wanted to buy. And he just wouldn't buy the car until he got to meet her. And finally, the salesman at Mercedes-Benz had to fess up and say, I'm sorry, you were talking to a computer. So AI ethics, maybe when you're talking to a computer, there should be a little box that says you're talking to a chat box, not a human or I don't know. I'm not an ethics person, but I'm sure at some stage of your life. I'm sure you've seen Google Assistant. Have you seen how Google Assistant can book a reservation at a restaurant? So if you type in Google Assistant booking a reservation at a restaurant, there's an incredible, like 1-minute conversation where the computer's talking and booking a table, and it's you know, it's not like phoning up United Airlines and going through a long list of being. This is like a real life. I mean, I couldn't tell it was a computer, right? So what's the ethics of that? You know, do we care that we're talking to a computer, not a human? Should we know that we are? ... So ethics are coming. Interpretability. Remember, deep learning is just a sequence of nonlinear filters, right? Very hard to go back and say, okay, well, what's the causal reason why A happened to B, or how do I interpret that, right? So, of course, all my economist friends absolutely dislike machine learning, right? They will fight it, and their argument will be, well, explain interpretability, right? You can't tell me why your system's working. Right? So I also find it amusing. I'm very good at looking at fields and realizing which fields like certain things and which fields don't, right? So I'm always amused at how economists just continuously do what they want to do, right? Even though they say they're data dependent, they seem to be the most undata dependent group I have ever come to see, right? You know, maybe they're right, maybe they're not right. I won't talk about digital twin models, but that seems like another topic that's coming. My book was about humans and machines, right? So maybe you guys will talk more about it. But yeah, there's still humans in every loop, right? Remember the original wall example I did? There was a lot of modeling in that wall example, or doing a probability map for searching for submarines, or I'm sure the work that all of you do here, right? There's still a lot of human input, right? You don't just come up with an AI system that does something magical, right? It's typically a hard problem that requires a lot of human effort. Okay, how exactly am I going to sort these things out, right? So, geez, I don't think us humans are finished yet. So, and in some sense, you know, if you've got a human making the decision, maybe this is a Vadim statement, actually. You can tell the Vadim ones are not right. Interpretation is always going to be an issue, right? If it's a Vadim, it's not an issue if humans made the decision, right? We could argue about that. I know a little bit about Google Deepmind, and I'm sure if you followed the news, AlphaGo was one of their algorithms, a reinforcement learning algorithm for playing this Chinese game Go. They used it in chess. They used it in energy conservation. They're now using it on medical data. So there's a Google Deepmind algorithm that takes a picture of your eye. Apparently your, I'm not going to get it right, but it's your blood cells are the smallest at the back of your eye. So apparently if you have an image of the back of your eye, it's much better than a blood test. The other thing I realized about the healthcare system is you go in and you think you're ill, and the doctor will ask you 150 questions, and then he'll say, oh, let me take a blood test. So I'm sure in the future it'll be, oh, let me take a picture of the eye. So there's an eye test they have, there's kidneys, pockets. So Deepmind is doing a lot of these healthcare analytics things. And I guess Florence Nightingale would be my original example. So maybe at some stage, pictures of eyes will take over it. Okay, well, I've left, I think, a good 10 minutes for questions.
Well,
so.
Actually, we can go until almost 12:30.
Oh,
But,
I thought it was
no, there was a very interesting example in your book about how speech recognition develops. But
oh yes.
How does deep learning or reinforcement learning, how did it actually perform the speech recognition? And if you could step us through that, I think that would give us an example of how this deep learning works.
So maybe just a step back a little bit, right? When I first started, there was just numbers, right? CPU. So all of our models would just say, take a data set of numbers and figure out a statistical model on numbers, right? I'd never really seen much image processing, which is again a 256 by 256 grid, right? And I'd never seen natural language processing, right? I'd never seen taken text. How do I put probability models on text, right? Well, Google has an algorithm called word2vec. So it takes a word, converts it into a vector, right? So there's a clever, so it's the reason I put this slide back. There's a clever non-linear transformation of words through a bunch of filters, right? To end up with a bunch of vectors, right? So how do I solve language processing? How do I do an NLP problem? I first of all have to construct a mapping from words to vectors, right? And that's a secret sauce. I think the Google, they have a couple of algorithms, right? I can't remember their latest algorithm, but it's, I think, like 150 layer. I didn't tell you how many layers you put, right? I think it's like 150 layer deep neural network, right? For doing, for converting words to text and doing the deep learning model, right? So the effort in it is, well, what nonlinear transformation do I do to get to a bunch of vectors, right? Now, once I have a bunch of vectors, I can start to do equations with vectors, right? So I can do things like king minus queen equals man minus, and it'll fit in the woman, right? Toronto plus Blue Jays equals Montreal plus Sky. Expose. See. Now, how did Chris get there in his mind, right? Did he take the words? Did he go through some complicated nonlinear transformation, convert it into vectors, and then go vector plus vector equals?
Yeah, I have a neural net up there.
250 layers, right? So a simple answer to you, Larry, is there's something called Google Word2vec. In the book, I describe it as 20 questions, right? it's a little bit like asking 20 questions, right? How do I take words, convert them into vectors, and then I can create paragraphs? I can write things. You'd be shocked at what people have done with that. Somebody took all the text of Game of Thrones, which I've never watched an episode because I'm too busy doing my deep learning papers. Took every script of Game of Thrones, fit their deep learning model to it, and then created a new script with a new ending, right? What other crazy ones have I seen? I mean, it's actually incredible what people have done with these deep neural networks.
So for example, in interpreting speech, I mean, it's not just being able to recognize the words; it's also the context and things of that sort. So how do they get that into their speech recognition system?
Well, the old models were like hidden Markov models, right? I've got a word here. I see what words are on either side. 20% probability this word is going to follow. 10% probability. So before they were like hidden Markov models, right? Now they just take a huge big data set, right? Pattern match. So you're finding that sequence of nonlinear transformations. So it's like a nonlinear embedding, right? And then from that, I'm not sure what the probability model is behind that, right?
Sure, there is one.
Well, it's just a sequence of these nonlinear transformations, right?
Okay, how would the pattern matching help them understand what the person's saying? You went through some nice examples in the book. I can't recall. You got to the point of the spectral algebra, and you said, okay, now when Google speech recognition is looking at a sentence, I was trying to understand what, from the context, what this particular word means, and it could do that by comparing it to something else. But yeah, you can't recall that. Okay.
Yeah, no, I can't. But, I mean, the original example is just back to in the 1970s. Brad Efron and Thisted took all the words of Shakespeare and just did like a Poisson distribution to fit the frequency of words that Shakespeare knew, right? He knew 250,000 words, and they built a little probability model of, if I see a bit of text of Shakespeare or a bit of text, can I identify whether Shakespeare wrote that or not, right? The Bayesian calculation, right? I'm not so sure that Google is understanding what people are saying, right?
Of course it's not.
But that's why I'm a little bit stuck at the. I mean, Google Translate, for example, is again just one of these nonlinear.
But speech
mappings, right?
Speech recognition. You know, if you're speaking to this bot who's the Mercedes advisor, I mean, they're understanding in some sense the question you're asking them and respond.
Yeah, but it's just a huge big matrix, right?
Okay. Can you explain a little bit what that? I have a little trouble visualizing a huge big matrix and an answer to a question, so you're going to have to give me the little transition.
Okay, let's start off with a data set, right? Let's start off with 100,000 possible sentences that could ever appear, right? Maybe more, right? 10 million, right? Massive data set, right? You could ask about color, you could ask about size, you could ask about engines, right? I started with a massive big data set, right? I fit a series of nonlinear transforms. First of all, I convert my words into vectors, word to vec. Then I fit my deep neural network to it. So now I just have an input-output map, right, that I've learned from my 10 million, or every single possible question that's ever come up under the sun, right? So it's a continuous living thing, right? It's like, I mean, Amazon Alexa, Google's Google Home is the same concept, right? I think
it's been trained on annotated data with the input questions and output responses, and then you feed it new questions, and it comes up with new similar responses.
In some sense, yes.
Otherwise, I don't know where the responses would come from.
I mean, it's human to human. It's trained on human to human chat.
Yes, I've got a huge data set I've started here, right?
And likewise, for your example of the Game of Thrones scripts, there's only been a fairly limited small number of Game of Thrones episodes, but presumably a deep neural net was trained on lots and lots of similar data, maybe other scripts, maybe other things, and then transfer learning was applied, where you take that trained network and apply it to the new inputs of, so it can figure out.
First of all, I never grew up doing speech recognition linguistics, right, or image processing. But I can see, and I don't do these problems, right, but I can see how the technology works, really, right? And I'm just trying to say that, I mean, it's okay. I mean, Google seems to me to have by far the best algorithms, right? So in all possible cases that I've looked at, Google Assistant versus Alexa, ask it a question, see what it says back to me, right? Now, to me, the way I see it is there's a trained data set of input-output questions here, right? That there's an incredibly large, big set of them, right? With some 150-layer neural network that is quote-unquote learned from its training data to some form of output, right? I mean, Spotify is the same way, play me a song, right, that I like, right? Go off and then it'll go back and ask me things like, did you like that song? Yes or no, right? So if you start to give a little bit more data, it'll cut up, it'll personalize it to you, right? To me, they're all just nonlinear maps from very large data sets, right? Maybe that's not a good way of.
To change the topic here a little bit. One thing about military situations that we typically deal with is they're complicated. Say you're trying to find a moving submarine, right? And you're going to have a certain amount of data from sensors to do that. Possibilities are endless what the submarine can actually be doing, but you'd like to characterize, you'd like to find it or characterize what its mission is or something of the sort. Typically, there's no data. I mean, very little data on similar military situations. So what do you do in a situation where there really isn't a lot of training data? Do you substitute physics?
Again, my guess here is that my prior distribution is like, I know nothing relative to the group in the room, right?
For like if you're trying to find a moving submarine, the prior distribution is on stochastic processes, possible movements of that submarine.
Well, for this to work, right?
But hang on, I'm saying that those models aren't driven by data. In other words, the actual physical observational data is very sparse. But yet we still have to build models for what the submarine might be while we're looking for it with real-time data. So my question is, and this is true of finance too, what do you do in a situation where there really isn't a lot of relevant historical
finance has way too much data, right?
Well, it depends upon the question you're asking. But we'll talk about that at lunch. I'm saying
no problem. Maybe
military situations are characterized.
Again, maybe let me make a prediction then. Deep learning will not take over from Metron, and you guys are totally safe.
No, it's real obvious. Look, I'm saying these are the problems we face. I'm not saying that this doesn't apply to a large class of things we do. I'm saying there's also a class of things we do where there really isn't any relative data or it's very sparse.
Well,
so what are you doing?
So the reason I'm hesitating there is data sets can be simulated data sets, right? So for example, suppose you have your favorite model, right? Simulate out a whole bunch of paths of submarines and X's, right? Just Monte Carlo, right? That's a data set.
But then the answer you'll be characterizing the simulation.
I'm just trying to say when you say there's no data.
Well, I'm saying actual observational data. Well, we talk about this all the time. Can we use simulated data or not? And my fear is always we're fitting the simulation, not the reality. No.
All I know is do not underestimate. Google has 6,000 projects that does deep learning. 6,000 different projects. All of my friends in image processing, Stu Gieman, Don Gieman, they used to model images. We'd do mathematical models of faces, eyes, noses, angles, the whole thing, right? Equations everywhere, right? Then along came ImageNet, 100,000 images. Along came a sequence of nonlinear transformations, came over. The natural language processing people used to hit in Markov models of trying to predict what the next word was going to be.
So I'm a statistician too, right? I mean, so if you have a lot of data and you've got a complicated nonlinear model, we can do some kind of fit that will probably make some sense. It's a big fitting problem, right?
Yeah, and all I'm trying to say is that they were very clever at finding labeled data sets, right?
What I'm saying is the class of problems that exist in the real world where there really isn't a lot of relevant data. I'm just asking what your philosophy would dictate in that case. Are we subduing?
Well, again, I'm making a prediction. You guys are fine. It'll never take over. But then I just realized I'm 0 for 4 in my prediction space.
I like your prediction.
You do.
Do not underestimate this idea of somehow. I mean, I'll do that. I know the chess games. I know Alpha Go quite well, right? How do they beat the Magnus Carlsen chess, right? It took 23 million chess games of experts. Chess has got what, 10 to the power 154 possible states, right? So for the Bellman equation people, 23 million is so sparse in the space of all possible. So many scenarios you've never seen, but they had their data set 20 million. They fed a stats model to predicting what would Kasparov do in the next move given this position, right? So they had a model of humans, right? Then they realized, yeah, let's just do a deep learning model on that. Then they had a deep learning model on the model of humans. And I was like, okay, well, I can basically match Kasparov, right? Then they realized, oh, the computer can play itself. Not 10,000 times, not 10 million. They can play itself 10 billion times. And as that simulated data comes in, it gets better and better and better and better. And it took 4 hours for AlphaGo to train itself on chess.
Do you believe that simulation can provide relevant data? That's what you're saying.
Not just relevant, it went from you watch it play chess now, and there is a I would like to say 10 to the minus 100 probability of Carlsen winning.
But your fit will be good to the extent the simulations are realistic.
Well, in the game, one is a pretty obvious objective, right? I just want to maximize the probability of
I
winning.
can do that.
Yes.
I'm repeating myself, but there are plenty of situations where you can't imagine a simulation. It's going to generate relevant data for a situation you've never really seen.
That is a huge field right now. I mean, people simulating realistic data, sensor response data, all kinds of sensors, from LiDAR to sonar, et cetera. In fact, I've gotten 2 calls this week about someone trying to convince me that to train the models, the deep learning models that we're looking for, we should consider their sophisticated simulators. And even for self-driving cars now, there's lots and lots of simulators so that you can train these models on situations that you just can't replicate in real world to the scale that's necessary.
See, now I'm getting worried, Tom. So Larry, now I'm getting very worried. NVIDIA has a simulator for doing self-driving cars, right? I guess is the.
So I think maybe we should wrap up. Something that Dan wants to say.
Well, it sounds like we have a few questions on that.
Okay. Very good one in the back too. But so the question online was, there are some papers in the past 2 years on Bayesian deep learning. Have you looked at these? And if so, have you formed an opinion on how valuable the approach is?
Deep learning, Bayesian, 2017. So yes, and I would like it to become more popular. Whether it will or not is again debatable, right? Actually, the TensorFlow, just back to the coding, that TensorFlow, no need for Bayesian in it, incredibly powerful on its own, right? But you know, it'd be nice if Bayesian deep learning took off, whether it will or not, debatable.
Do you have other questions back here?
I have. So one of the issues comes down to when you process the data through all these different transformations and so on. Ultimately, you're always going to get an answer. You give it an image, it's going to say what it thinks it looks like.
Yes.
What you really don't know is in the training process, what parts of that image space were well sampled and which ones weren't. The catch is no matter what you do, that model's always going to give you an answer, but you don't have a good sense of how confident it is in that answer. I mean, it kind of gets back to this base.
The Bayesian one.
Yeah. So just what's your take on, remedies for, or at least how the community is trying to address this issue?
You can see it's the beginning of a field because these questions are so hard, right? I mean, a simple answer would be the stats answer. Well, of course I want I want Bayesian posterior regions, right? I'm not so sure. I'm becoming more of a machine learning AI guy than a stats guy. So
but still, I mean, getting back to the question though, ultimately, is it informed or is it not informed in terms of what the answer is given? If I give it an image in some part of the space it's never really seen before, it may be confident that what it's seeing is a dog, but in reality, it's never seen any image that looks like this. It just so happens to the way the decision boundaries are, it's in the dog part of the subspace.
Oh, you're 100% right? I mean, there's generative adversarial networks, GAN models, where people are beginning to realize that, oh yeah, you know, how do I find an image that the system's not going to classify well? There's the whole issue of, do I even want anything in a black box? I've talked to some people like, come on, if it's a mission critical system, I'm not putting anything into a black box, period. Right? So, I mean, you can, I'm sure we can go along the, not just the interpretability bit, but to the bit that, you know, but for me, it's incredible how the image processing, I mean, all my friends used to work in image processing, right? And, you know, there was a lot of research from the stats perspective that sort of just disappeared, right? The natural language processing, I don't know that much about, but again, you know, I can ask my Google Home a question and it'll even start to answer back to me, right? Oh, Nick, did you like that song? Oh, good job. It'll start to, you know, converse with me. Now, how it does that in the back of my mind is, yeah, I turn words to vectors, and there's more than one way of doing that. And then I've got some incredible world database, you know, and out it comes an answer, right?
So what I'd like to do, folks, is have Nick wrap up the formal part of his talk. Those folks that want to stay and ask questions can stay. So Nick, thank you very much.
Yeah, cheers. Thank you. Thank you for having me.
Thank you again for coming and spending the day with us and being receptive to our pointed questions. We'll have plenty more for you over lunch and hopefully later. We do have a couple Metron mementos for you as a way to say thank you. And also, when it comes time for you to give your talk on David Letterman, you'll remember us because you're not going to be there with Metron on it. So very, thank you so much.
Thank you for coming.